Well, I hope it's obvious. The first thing is read it, right? And outline it. Highlight it. This is what you're doing tomorrow. You're going to come in and you're going to do this for 80 minutes tomorrow. The more you understand about what you're doing, the better you understand it. The better the result. There's no question that if you come in tomorrow and you're looking around and you literally are sitting there like, I don't know what I'm doing. I got some acid in here, some base there. Where am I supposed to do next? Where am I supposed to go? What numbers am I collecting? What is it? Drops of what? What am I adding to what? How am I supposed? No, there's no time to do that tomorrow. Tomorrow you're coming in, getting your safety equipment on, getting your small groups, and doing the lab. And collecting the data. That's all you have time to do tomorrow. It will take you all period to do it if you do it well. And then doing the calculations, because you're going to have to calculate some things. That's what you're going to have to do. You don't have time for all the rest of that. So read this. Read the background so you understand what content. Read the safety so you understand what safety hazards there are. And there are safety hazards. You will need gloves. You will need goggles. You will need aprons. This is acid and base. This is hydrochloric acid and sodium hydroxide. I tell you in here how I try to minimize the danger. I have a lower concentration of base. You don't know the concentration of acid. And obviously you're wearing goggles, gloves, and aprons. That's the plan. So then I start giving you some backgrounds. Notice that I have space here for you to do what? Summarize. You might want to add some key words or ideas like, oh, maybe the acid's going to be here in the water. It's going to be dissolved in the water. Or not. Maybe you don't want to add that. Let's water. So water's a polar molecule. It has a positive side and a negative side. A positive side and a negative side. And so what that does is it allows it to dissolve things. Yeah. Yeah. So when you have a glass of water, you have two hydrogens connected to oxygen. The hydrogens are partially positively charged. The oxygen is partially negatively charged. So two sides, two poles, a positive pole and a negative pole. That's why we call water polar. So this is polar. When you take and add sodium chloride is an ionic compound the way you learned about them yesterday. And they have a positive and negative side. They have a positive ion, chloride, and a negative ion called chloride, and a positive ion called sodium. In solution, what happens is that the oxygens line up around the chlorine or the chloride, and the sodium, the hydrogens. That's not right. Excuse me. The oxygens line up around the sodium, and because the negative attracts the positive, and the chloride gets attracted to the hydrogens. So you get what's called hydration or dissolving. That's what dissolving means. You see the sodium chloride, the salt disappear, but did you ever wonder where the salt went? Did that not ever occur to you? When you dissolve salt in water, did it ever did you ever ask the question, where did the salt go? Did you think the salt was destroyed? Was it changed? The water surrounds it, surrounds the sodium, and it surrounds the chloride. It's just that they line up differently. So what you get is the sodium and chloride are dissolved in water, and you don't see it anymore. How do you know it's still there? How do you know sodium chloride is still there when you put salt in water? You don't see it. How do you know it's still there? You can taste it. If you drank salt water, you'd know right away. So when you dissolve salt water, it dissolves. It's still there. It's just that the water surrounds it and makes it go into solution. This is a physical change. This is just mixing it up really, really well. It's really just mixing up salt really, really well with water. That's all you're doing. That's it. So let's move. The chapters are in your syllabus. Let's go look. Yeah, look, the one that I have in the calendar, right? If you look at the, let me go to it. Where is it? It would be drive.
Did you say it was due tomorrow or tonight?
Oh, I don't want you to take the chapter reading notes. No.
Oh, no? Just read it over?
No, see here it says chapters 1 and 6 is what you guys should be reading throughout the whole. You have all the way up. You should be reading it.
So should we not take corner notes on it?
If you want to, I think you could. I would. What I would do is I would read on it, and anything I found that was related to what we talked about in class, I would add it. I would use it to revise the notes. But I might assign the chapters one day to say, by next week, by Monday, I'd like you to read chapter 20, and I don't know. Does that make sense? But no, I have not assigned it. No, I've not.
Do we still get credit for the assignments that you gave back to us?
Yeah, upload them.
The rat one, the waterfall one, do we still?
Wherever they go. It could be in the rat one, or it could be in the waterfall one. There's assignments like this assignment's in the waterfall one. Safety contract, safety test is in the waterfall one. And the other assignments are in not in the waterfall, in the rat one. All the other assignments in the waterfall.
Okay.
See, look here. Let me show you. So the assignments, for instance, this is the waterfall. These are the 4, let me go to materials. And so in the first week of class, you have these assignments, right? And then Monday you had this assignment. Then you had notes on this, right? But I haven't collected, I don't think. So that's what shows up in the grade book here, right? Now, when you go to the other course, the RAT, in the lab, you have lab safety contract, lab safety test, titration lab. Now you got these 4 assignments there.
So we gotta upload them all to school that you to get credit for them?
Yeah, uploaded all the schools, yeah.
Okay.
All right?
All right.
Could you tell the rest of them? Because they must not have been listening too, because you were all too busy talking.
Got it.
I don't know. Here again, some room for you to summarize. What is this all about? Water and pH. What is pH? What's hydroxide ion? I already added positive charge, negative charge here. The positive charge is which? The negative charge is which? You could just add that. So this is the kind of stuff you could do with these handwritten. You guys did the activity yesterday. You took notes. Either you did or you didn't. Go ahead and talk about water. So here you're talking about hydroxide ion and oxygen bound to one another. So OH has a negative ion, the OH looks like this is an oxygen. Its bond is sharing with a hydrogen, and then it has this many electrons. So everybody has a full octet, but there's an extra negative charge on it. That's not very stable, but it's one of the simplest definitions of a base. This is what a base is. How much of this you have. If you have a lot of this, you can only have a lot of this or a lot of acid. You can't have both. You can have a lot of that or you can have a lot of H+. Either a hydrogen ion or hydroxide. Hydrogen ions are known as an acid. So that's what an acid and a base is. A base is having a lot of this. Oops. And an acid is having a lot of this. That's the simple way of thinking of it. Now, a lot in a solution. Now, what happens if you have a lot in a cup? If I have a lot of hydrogen ions, if this is an acid, very strong acid, a lot of it, and I go throw it in Lake Erie, what happens to that? Is it still very acidic once it mixes with Lake Erie? You think it is? Let me ask you a different way. What if I had some Kool-Aid in here? It's really sweet. Then I take that, or you know what? What's a better? Anybody here drink soda pop? What kind of pop do you drink? What is it? Pepsi. So if I take a 40 ounce, 1.2 liters of Pepsi, and I take that and I dump it into a swimming pool of clean water, and I drink it, will it still taste like Pepsi? Is it strong? No, it's diluted, right? It's not as sweet, it's not as dark, it's not as cola flavored, right? In fact, I probably wouldn't even taste it. Does that make sense? It's so dilute. So how acidic something is depends on how much acid there is, how much H+ there is in the volume, or how much OH there is divided by the volume. In how much. So if I have 10 hydrogen ions in only 1 milliliter, maybe that's a lot. If I have 100 in 1 milliliter, then that's even more, isn't it? So the more of this I have in a volume, the more concentrated the acid, the more of this I have in the water, the more base it is, right? Well, we're talking about things we can't see. The cola, at least it was dark and you can see how dark it was. But this you can't see at all. It's transparent. These are, H+ is a single proton. You can't see it. Gentlemen, focus. You can't see it. So how do you take a glass of something that you don't know? You're going to see an unknown acid, an acid of unknown concentration. You don't know how much hydrogen ions in there. How can you tell? How can you figure that out? That's the question. How strong is that acid without having to stick your finger in it? How strong is that acid? Well, first you should know this number. That number is known as a mole. 1 mole is this number. Somebody says, I have a mole of something, they mean they have this number of that. All right, that's a big number, but that's what it means. But does everybody agree nobody wants to write that number out? Right? Yeah.
Can't you just like a line over one of the zeros?
No, because it's not infinite. There's actually a decimal at the end of that. So you're right. I could have just, if it was like one of those repeating zeros after the decimal, you're right, I could do that. Well, what we could do is do this, 6.022 times 10 to the 23rd power. That's a lot easier to write. This is called Avogadro's number. So when you have a mole of something, you have 6.022 times 20 times 10 to the 23rd of something in a certain volume of something. So you have, for the base, the sodium hydroxide, for the base, you know what the concentration is, 0.1 molar. That's the concentration of the base you're working with tomorrow. That 0.1 molar base means that you have 0.1 moles over 1 liter. So you have 0.1 of this, which is still a really big number, right? I mean, if you took this and multiplied it by 0.1, it would still be a really giant number. Do you agree? It would be just 1 less zero. That's not a big deal. So 0.1 molar, 0.1 moles per liter. That's your base. So that tells you how concentrated the base is, but that still doesn't get you to how concentrated the acid is. To be able to understand that, you have to understand but let's go ahead. Yeah, one more drop of OH negative. What is it? It's a base.
Chapter do we read?
Notes. And you could, here you already pretty much have the summary. Here you have almost all of it written out. Maybe you add some things like, why are we adding the phenolphthalein? Right? But there's the answer to that there. What we're talking about. And how do these things react with each other? And as you can see here, the acid defines sodium hydroxide is 0.1 molar. You're going to add a drop of phenolphthalein. It's going to, this is not right. You should not add phenolphthalein here. So this is incorrect. Make sure you correct that in the lab. You should not add any phenolphthalein to. Does it say that in that lab? Does it say it there in your lab on that page? Yeah, scratch that out. You should not add phenolphthalein to the sodium hydroxide. You should be adding it to the acid only. I don't know why I keep making that mistake. I just must have been having a really bad day. So just scratch that out. That should not say that. So when you're doing the lab, it should say you want to have it's going to be a clear solution. You're going to add. All right, so this whole thing is, I don't understand why this page is even still there. Can I erase that? I wonder. No. This whole thing is also wrong. It got reversed for some reason. was having a bad day. So make sure you don't make that mistake. The phenolphthalein is an indicator that will change color if it comes into contact with a base. So you're adding the phenolphthalein here. Let me add it to a different color. The phenolphthalein is being added to the acid. Because as long as it's in the acid, it's clear. Once the solution turns basic, it changes color. All right. You know the concentration of the sodium hydroxide. You're adding the phenolphthalein to the acid so that when the acid and base change, once it becomes NaOH, once there's more OH present, once it becomes a base, then you have a changing color. So, as you can see here, when you mix HCl, hydrochloric acid, with sodium hydroxide, the hydrogen mixes with OH and becomes water, H2O. And chlorine and sodium come together to form a salt. So you get salt water. It's neutral. This is a neutral solution, so this is pH of 7. When the two volumes are equal. But what if you add a little bit too much? What if you add a little too much to the acid? A little bit too much base to the acid. What's going to happen? So let me be clear. You have this beaker has NaOH, and here you have this acid HCl, and you start to put drops of sodium hydroxide with and in here you also have phenolphthalein. You keep adding drop after drop after drop, and you're counting how many drops you're adding to the HCl. And when the volume gets equal, when you have added equal amounts of hydrochloric acid to sodium hydroxide, it's going to become neutral. It'll become a pH of 7. But what happens if you add one more drop beyond that? No. It'll be unbalanced, that's true. But would it be more H plus or more OH negative? So no explosion, God will help us all. What would you expect if you had one more drop of OH than H? You're right, you have too much OH negative. So what would it be, an acid or a base? Well, let's go back. I know you just learned. So you have a base. So this is a base. And so when this solution turns pink and stays pink, you have to keep mixing it. You're going to have to keep mixing it to make sure that it gets completely mixed. But when it turns pink and stays pink, that's a base. Now you have, that's one, so it's not equal. So you want the number of drops right when they're equal, when the stuff was neutralized. So you want the number of drops. So you're going to have to count how many drops. It changes color. Then you're going to subtract one drop. Does that make sense? Yeah. Yeah. And we'll talk about it in a minute. So so you have some idea. See here, it says it correctly. You add Yeah, this is, again, I don't know what happened. Why does this must be the old one. Does this also say add NaOH with indicator? The NaOH does not have the indicator. The acid does. I don't know what's going on. Yeah.
In the beginning, it says we would use the language to identify the words. Do I press that after like mistakes?
It does. You should change it. I don't know what happened. I swear I corrected all that. But definitely, you're wait, say that again. You use phenolphthalein.
We would use phenolphthalein to identify the words.
That's correct. No, that's correct. We identify the base with the phenolphthalein. That's why we don't put it in the base, because if you put it in the base, it just is pink. Then it's pink right away. Then you're waiting for it to turn clear. And it'll never do that. All right. So it's not clear in a base. See how it says here it's clear in a base? That's wrong. That's so embarrassing. I swear I thought I fixed that. Clear in a base. It's pink in a base. And it's fuchsia in an acid. And it's fuchsia in a base. So it's clear in an acid. And in a base, it's fuchsia. Make sure you correct that as well. Wow, I thought that gives me even a bigger headache than I had when I started. All right, so make sure you correct that as well. So it's clear in an acid, and it's in a base, it's fuchsia. It's like a pink-red color. It can turn pretty dark if it's really basic. Are we good then? All right. The chapters. Each of the pages is written in Cornell Notes. Wherever you see there's a spot for you to summarize, you might want to summarize. Wherever you want to put down, man, this is step 1. Maybe you go ahead and add, step 1 to it. Or do first. Something like that. So that I see that you've read it and you know what you're doing. This is evidence for me that you know what you're doing when you're doing it. Otherwise, I'm worried you're going to hurt yourselves tomorrow. So that you got to calibrate your dropper. You're going to have to answer. Here's a question for you. You know what? That's something you might want to answer. That could be something you could answer there. That would kind of give evidence that you've actually read the lab. You can summarize why you're doing this and answer why is the same person doing this. Some of this now. See if there's any mistakes here. All right. So the first thing you got to do when you do the lab tomorrow is you're going to have to make sure that you know how many drops equals a milliliter. How many drops equals a milliliter? That's what you're trying to find out with this first step. So you're going to have somebody with a dropper. One of your teammates with a dropper is going to sit or stand. Everybody's standing. He's going to stand and drop drops of water into a graduated cylinder. And you're going to measure when it gets to 1 milliliter. As soon as you get enough, let's say it takes 50 drops, it takes 10 drops. The first time you do it, it takes 10 drops to get 1 milliliter. Well, in this case, some of the graduated cylinders won't say 1 milliliter. The lowest measurement they'll have will be 2 milliliters. Some of your graduate cylinders, the lowest number is going to be 2. So if it takes 10 drops to go to 2 milliliters, then how many drops per milliliter? 5, yeah. So it'd be 5. So you see here, that's what I did here. If it takes 10 drops to get to 2 milliliters, then it would take you 5 milliliters For every 5 drops equals 1 milliliter. If it takes, then the next time it takes 12, that would mean 6 drops equals a milliliter, and the next time it's 15 is 7.5 drops equals a milliliter. Add those up, divide by 3, that's your average number of drops per milliliter, and that's the number you need. You need that number. Are we clear? Does that make sense? That's your goal for step 1. As soon as you come in, after you have your safety equipment on, that's the first thing you're going to try to do is count how many drops to equal a milliliter using just plain water. You're going to need that number in the future. And why is it you should, why don't we go ahead and answer this question. Why should the same person who's doing the water drops be the person who's doing the drops of base into the acid? Say what? They remember what they did, right? And why is that important? Exactly. You guys got it right on. So they remember how much force they use, and they're going to use exactly that force again so that you get the same size drops. If the drops are bigger or smaller, then they won't be the same number of drops for 1 milliliter. And you can end up getting a bad volume measurement. Are we going now? Is that what's going on? People are putting bags. When is it? Class over already? Did I take attendance? Is class over, first of all? How at 58?
48.
Oh, 48. So, but I need to take attendance, don't I? All right, so quickly, are you reading? Here are the steps. The problem here is that phenolphthalein is not being added, so this is not right. I don't know why this is still on there. Oh, no, I did that right. So you're adding the phenolphthalein into acid because when it turns basic, it will change color. So when you add this to this, when this turns basic, it changes to a different color. A pink, and you can read it here. Go ahead and do. Let me see if there's any other mistakes. See, from then on, I think I corrected it. So I think it's all corrected after that. See how I changed it there? All right, so it's... I can't stand when I do stuff like that. Alexander, you here? Ah, wrong class again. Adams. Bailey. Sierra. George. Benning. Jamal. Oh, that's you? You guys got to stay here. I got to mark you absent. Oh, not here. Okay, thanks. I thought you said you were here. Butler. Thank you. Chandler. Cashmere. Absent. Colbert.
Here.
Collins.
Here.
Zaire.
Here.
Grant. Trenton. Christian. Hall. Amaya. Absent. Henderson. Rayana. Thank you. Hicks.
Here.
Knott.
Here.
Lee.
Here.
Menifee.
Here.
Merrick.
Myrick.
Myrick. Yes, you're here. Reed.
Which one?
Good question.
Janae.
Janaea, thank you. I was going to say Janisha. I knew that was wrong. Janaea. Hey, I said I knew it was wrong. Janaea. Keyshawn. Sincere. Sincere, you here? Marking you absent. Tyrell. Marking you absent. Walker. Williams. Delilah. Absent. Woods. Yusef. Zelada. All right, guys. We still got 2 minutes, so hold on. All right. We still got 2 minutes, so just 2 minutes. Ladies, just give me. Ladies, just 2 minutes. So you get one. Guys, excuse me. Just a second. So you don't have to take notes, but just quickly, these should all be correct. You should have. Your job is to figure out what the concentration is. Now let's go through them. This is how you're going to do your calculations. How you can. No, I say we're about to talk about all these calculations in this Prelab. Things out. So pay attention to the math. You're going to have to do that tomorrow. There's that Avogadro's number again. Thank you. Second. Does that make sense to everybody? So that's what you're doing with them. And it goes through, and you should be able to hopefully understand. All right, so get that straight. And tomorrow you're doing the lab. So be here ready to do the lab. You have no time to be late. You still got a minute. Now you can talk your talks. You make sure your area is clean before you leave.
Us the papers back so we could like take a picture and turn it in. Remember that one thing in the first week you said like take notes on the 6 R's and stuff? You never
That was
gave
extra
back.
credit. I scanned it. I did give it back, but you must have grabbed it. Did you check here?
Yeah, I can check. And I don't remember you telling us to take notes on chapter 1.
Yeah, you can go. Did I tell you? Is that one of the assignments?
Yeah, I mean,
I never. Did I say? I don't know.
You just said on that list saying get these stuff done. It said.
Oh, let's about ions. So we just saw what happens when things form partnerships. But let me ask you something. If you had to have $100,000 to start your business, and you had $99,999, you need that one more dollar. And someone had $1. Would you make a partnership with that person for $1? No. Well, what atoms do is they snatch the $1. They take it. All right. It turns out that the elements they take it from want to give it anyways. They don't want the $1. So let's take a look at a simple one. You know what? I'm going to use the example of one that we see in the lab, tomorrow's lab. So chlorine has 7 electrons. Sodium only has 1 electron in the outer shell. These are all outer shells. These are called Lewis dot diagrams. They're only the valence electrons. That's all I'm putting. They have a lot more electrons. We're only looking at the outer shell ones. Chlorine just needs 1. Sodium doesn't even want the one it has. It wants to give it away. It has to do with how much. The reason it wants to do that is because underneath that first layer, that outer layer, there's an inner layer that's full, and sodium's not strong enough to pull in other electrons. So by getting rid of that one, it has a full outer shell. So what happens is, it's not ideal, but they take it. Chlorine takes it, and it forms Cl minus. chlorine with a negative charge, full octet, and sodium with a positive charge, full octet. The two of them stay near each other because they minimize the impact of having a negative charge. We call this table salt, right? The salt you put on your fries is NaCl, sodium chloride. Now let's take a look at another molecule. The molecule, this is not a molecule. Salt is not a molecule. There's not a partnership. Something got stolen. These are ionic compounds. Say that again. That's why it'll kill you. Salt's impact on the body. This salt is needed. You need salt, but too much salt can give you high blood pressure and it'll kill you. So oxygen has 6 valence electrons, so it can form 2. An interesting thing is it forms 2 with hydrogen. Hydrogen is strong enough that they have to form a partnership to get that full octet. But it's not an even partnership. It's a partnership where one oxygen is stronger than the hydrogen. So this is more of a hydrogen is less strong. So this has a partial negative charge, and this has a partial positive charge. And because of that, they call this molecule a polar bond. These are polar bonds, and this is a polar molecule. What that means is that there's 2 sides. There's a positive and negative, like the North and South Pole, like the plus or negative side of a magnet. Plus or minus side of a magnet or South Pole. Now, why is that interesting? Because when you form water, all water has this negative side and this positive side. When you form water, it will surround the positive. So here's this little positive sodium and a positive chloride, and this will get surrounded by the oxygens. And the chloride, oh, I can't believe it's not going to let me. All right. The chloride will get surrounded by the hydrogens. Does that make sense to you? Does it make sense to you? And the reason that happens is because water is polar. It has a positive side and a negative side. And so the positive and negative sides align. They form a pattern. They form a pattern that allows for hydrogen, the positive side of hydrogen to point towards the negative side of oxygen to point towards the positive sodium. And that's called dissolving. That's what dissolving means. It's a physical change. It's still salt. How do you know it's still salt when it's in water? How do you know? If I had put salt in water, how do I know the salt's still there? No, it dissolves. You put it in, it dissolves. It disappears. You don't see it anymore. Okay, you mix it up. It's not cloudy anymore. It doesn't look like there's anything in there. You taste it, and what is it? Salt. The salt's still there, but you can't see it. Well, where'd the salt go? The water surrounded it. It hydrated it, dissolved it. That's what dissolving means. Dissolving is a physical reaction. It's not a chemical one. So you're mixing it. You're mixing it really, really well. It looks like it disappears. And sometimes it can get cloudy depending how thick it is. But for the most part, it disappears completely. That's why everything that's in a clear bottle around here is not water. It could be hydrochloric acid. It could be sodium hydroxide. You don't know, right? So don't assume it's water just because it's clear, okay? So dissolving, water is really good at dissolving because it's polar. It dissolves ionic compounds. This is going to be very important in biology that you understand that water dissolves so anything that's ionic, anything with a negative or positive charge. It dissolves it. If that ion's going to float around. Are we clear? Then you understand what an ion is. Yes. Yes. I need to take attendance. I need to see who's tardy and who's not. So if we're done here, if everybody is so caught up with this much, we'll go ahead and start to take attendance. You guys can start on that list that you should have gotten done. There's a list of things you should have gotten done, right? Did you write it down, the list? The reflective list, and start getting it done. Someone turn the lights back on. Those of you that are tardy, come here. We're going to have a quiz. When is this class over?
Right now.
Wait, when's it over? What time exactly? Well, there won't be a... here's your quiz. Write it down on a half sheet. Everybody. Sorry, guys. Late guys are going to have to wait. Here's your quiz. On a separate sheet of paper, you're turning in, and that's your exit ticket. That's going to be attendance for you. I need the tardy passes. You ready? I'm saying it. You write it. Describe a covalent bond. Describe a covalent bond. Make sure your name's at the top. Label it quiz, and put the date. As soon as you're done, you can turn in here and go. No notes. Describe a covalent bond. You confused me. I didn't know whether to say yes or no on that. All right, go ahead and use your notes if you want. Most quizzes, you won't have notes. That's why you should be reviewing them every day. As long as you describe it, you're good. Whether you give examples, fine. It would give you extra. Alexander?
Here.
Layla?
Here.
Betts?
Here.
Exaria? Billingsley? Huh? That's it, just one. Aiden? Crawford? Dent? Dent, I need to see you. Finley? After you're done with all that, put your stuff away. Where's Finley? Thank you. Fudge? Thank you. Were you on time, Fudge, or are you late? Yeah, okay. I thought you were on time, but I wasn't sure. Hamilton?
Here.
Yeah. Saad? Hamouche? Hamouche? That's you. Say what now? Yeah, put it over there in the corner. I'm not taking responsibility for it though, right? I'm just saying, somebody takes it. It's not my fault. Hudson. Hey, how's it going? I'm in the middle of something. Where are you, Hudson? All right. Hurt. All right. Jacob. Where are you, Jacob? Let me see your face, Jacob. Oh, you're Jacob. Oh, yeah, Jacob. Marble. All right. Pounds. Thomas Mallet, and Williams, Kimberly. All right. I took attendance. I marked you late. Oh, here, just give it here. Do you understand you need to be in the seat in class at 8? Does that make sense?
I get here around 8, the lines are taking
Oh, the line's taking a long time. So try getting here a little earlier, maybe.
Mr. Mendoza,
I understand it's rough,
about my
but that's all. I can't do anything else. I have to start on time. I can't be waiting until 8:10 to start. I just can't.
I emailed you about my asynchronous quiz. Do you want me to come out at lunch?
Unfortunately, your lunch, I have class. After school, quickly.
Okay.
Oh, let's talk then. Come here. What I want to talk to you about? What is it? Do you know any issue? There's some issue that popped into my head when I saw your name. Were there absences or late work or something? I don't know. It's something came. I saw your name and it just popped into my head. I needed to talk to you.
Oh, he's back.
Oh, ready.
Mr. Mendoza.
Jacob, missing a lot of words. What is it then? All right, I can't remember. I'm sorry. Have a good day.
What's up, Mendoza?
What's going on?
Mr. Mendoza, did you want me to say after or before school tomorrow so I can do the lab safety test? Because you said I can start the lab stuff.
Take it now. Do it now.
Can we give you this?
Take it home. Bring it back to me. Done. Make sure you got a contract too.
Yes.
That's the last safety test, yeah. And that's the contract. Yeah, turn your quiz. Why are you late every day?
It's because there's a lot of traffic and it's kind of complicated.
Okay, well, try to make it here. I mean, I know you're stressed. It's not your fault because you're not driving yourself or anything, but try to make it here, okay? What class are you going to?
Computer science. I
Mendoza.
couldn't turn in any of my work on Schoology because it wouldn't let me sign into any of my email accounts.
Seriously?
Yeah, it says like my password was changed
Could you
6 months or 40 days ago.
could you try and talk to Mr. Krishna about that?
Alright.
Here, hold on. I want you to see me and that's in all your classes? Don't you have Dr. Adams?
Yeah.
Talk to Dr. Adams because he says you're all online. You're all ready to go. You all can get into Schoology. That's what he said.
I could get into Schoology, but whenever I try to email myself with pictures, it's not letting me log into the emails on my laptop. And
Why are you? All right, we're gonna have to talk.
camera on the laptop is too blurry. You can't see anything.
No, I understand. I understand that part. Why don't you just upload it directly from your phone?
It's not giving me the option.
All right, so you need to see me or Mr. Krishna. All right. Or
Mendoza. Is this okay?
yeah, but I just don't want a mess. The kids tend to make a mess. You know what I'm saying? You can leave it there. If it's a mess, I just have to get rid of it all.
Ooh, no, give it back to me.
No, I mean all of it. The whole corner has to go. I can't be having kids leaving messes. I'm already mopping the floor and the tables. That's enough. All right. My handwriting. Okay. So in the lab, you're going to be taking phenolphthalein. Yeah. Could someone please turn off? So you're going to take this phenolphthalein and you're going to add a drop of it. It's clear. You're going to add a drop of it to an acid. Now, I made a mistake in the previous version of the Prelab and I put into the base. Don't put in the base. In acid, it's clear. So it stays clear. You don't know what the concentration of acid is. Now, the question you're going to have is, how do we find out what the you don't see anything in there. It's a clear liquid. So the problem you're trying to solve with this lab, yeah. The notes I'm doing right now? Yeah, you should have in Cornell notes form. It's a good question. So this is an unknown concentration. What does concentration mean? How much of something is in a volume of something? That's what this divided line means, right? The fraction. How much of a thing is in a volume of a thing? That's all. That's what concentration means. But when you're talking about acids, you're talking about hydrogen ions, protons, floating in a glass of water that are invisible to the eye. There are these protons. How many of these are in any particular sample of this beaker? I don't know. Say what? It's an unknown concentration. We don't know how much. So, by the way, this is HCl. It turns out the hydrochloric acid in water turns into chlorine, a chloride ion, and it's a strong acid. So what happens is that the hydrogen and chlorine separate, and you get three things in that water. You get H plus, H2O, and Cl minus. Bless you. So that's what's in there, but you want to know how much of this is there in there. I don't know. I don't know how much it is. And there's a lot. I know there's a lot of them. They're molecules, so there's a lot in a glass of water or a beaker of water. So we use this number. That's the number of hydrogen ions that we assume. This is what we call a mole of something. 1 mole of something is that number. Now, do you agree that nobody wants to write that number out?
Yep.
All right. So what we write is 6.022 times 10 to the 23rd power. Scientific notation. It's much easier to write. It's also known as Avogadro's number. So Avogadro's number is a really large number. It's 1 mole. So the question is, if I know that, now what happens if I know I have an NaOH, sodium hydroxide, that has a known concentration. It has a concentration. We write concentration by putting square brackets. Square brackets mean concentration. So if I tell you that this is 0.1 moles per liter, we also scientists are lazy. We don't want to keep writing moles over a liter, so we'll put 0.1 molar. That's what molar means, moles per liter. So 0.1 times this large number, still a big number, molecules of sodium hydroxide in this liquid, in this known liquid. This is the known. So we know what this is. We don't know what the acid is. Does anybody know what happens when acid and base comes together? They react. So HCl, hydrochloric acid, when added to NaOH, does that make sense so far? No issues with that notation? HCl, which is an acid, combined with NaOH, which is a base, and this means combine. This means combine. Everybody okay with that? I'm adding the two together. So when that's going to yield, there's a symbol for yield. Result in, another word for yield is it results in a change. This change is reversible, so it's going to have a double arrow, one going one way, the other arrow going the other way. What's going to happen is that the H, the hydrogen, is going to be released. It's H plus, mixes with OH negative. H plus comes together with OH negative. When they come together, what do you think they're going to make? Let me redraw this. Can I redraw it with the Lewis dot like we just looked at a minute ago? So here's oxygen. Boom, 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 boom. There's hydrogen, and then there's one extra electron, and then one extra electron. So this is negatively charged. Here's H plus. What do you think is going to happen? Do they want to be positive and negative? They don't want to be positive. So what are they going to do? They're gonna combine. They're gonna form a partnership. They form a bond. So the negative and positive go away, and they share two of the electrons. So now they're sharing these two electrons. That's what these lines mean. These lines are the sharing of those two electrons. So now what do you have? We used to have HCl. What do you have now? And you had H plus and OH negative. What do you have now? What is this? Water. H2O. So now the OH, the H and the OH go together and they form H2O. Then the what is going to happen? The Cl and the Na are going to go together and make what? What are Na and Cl going to make? Huh? Na is sodium. It's a Latin for sodium, and Cl is chloride. So this is sodium chloride. You know it as what? Salt. It's table salt. So the sodium chloride in water. So all you're going to get is salt water. This is called the neutralization reaction. Here the OH and H are equal, so this is a pH of 7. Acid has a very low pH. Base has a very high pH. The two come together and form a neutral pH of 7. That's why it's called neutralization. Are we good? We understand each other? That's the reaction you're going to do. You're going to take advantage that for every mole of this, for every mole of HCl, I need a mole of NaOH to neutralize it. Does that make sense? Do you see how it's 1-to-1? You don't see it because they're oh wait, what time is it? Time to go? Is it time to go right now? All right, peace. Go, get out. Go, go, go. Sorry. I don't want to make you late. Come here and ask me a question. Continue reading. All this is being recorded. I'll post it. But okay. You want me just to post it on Schoology?